Let's talk about what we mean by the solution of a linear system, because it's possible that there could be many solutions or no solutions. So actually what we mean is, what is the set of solutions? So the solution set of the linear system ax equals b is the collection of all vectors u such that when you substitute them in place of x, so au, you get b. The system is inconsistent whenever the solution set is empty. So this is sometimes written as the empty set. And denoted with this circle with a slash through it. Maybe there's a slightly better one. Okay, so to give you an example, suppose we have the following 2x2 system, and we need to solve ax equals b. So we make the augmented matrix A bar B, and it's 1, 1, bar 1, 2, 2, bar 1. It looks like this, and we can do a row operation of maybe doing minus row 1 added to row 2. And, I'm sorry, not minus 1. We're going to subtract 2 copies. So subtract 2 copies of row 1 from row 2. So then the first row is going to not be changed at all. And then we're going to have 2 minus 2 is 0. 2 minus 2 is 0. 1 minus 2 is minus 1. So let's take a good look at this last equation now. Now the top row says x plus y equals 1. The bottom row says 0x plus 0y equals 1. Or in other words, 0 equals 1. And that cannot be true. That is a definite contradiction. So that means that there are no solutions to this system. So the conclusion is that the system is inconsistent. So what kind of possibilities can there be? Well, let's take a look. For a 2x2 system, we can have any of these possibilities. So the first one is like our first example. And it corresponds to a unique solution. The second one is like our second example, the one that we just looked at right above. And in this one, we had no solutions. So the solution set was the empty set. And that's because the two equations described geometric objects, curves, that have no intersection. In this case, they're straight lines that are parallel, so they have no intersection. And then there's a third example that we haven't done yet. That would be, what if A looked like 1, 1, 2, 2, and B looked like 1, 2. Well, in this case, the augmented matrix reduces to a row of all zeros. And so what we end up with is just a single equation, and there we have just a single equation. And so actually what this shows us is that both equations that we had define the same line. And so in this case, there are infinitely many solutions, because any point on the line will work. So the conclusion from all this is that there can be 0, 1, or infinitely many solutions. So the solution set is going to have nothing in it, or one thing in it, or an entire infinite numbers, an entire line's worth of things in it. And this continues in dimension 3. So here's an example of different kinds of configurations that one could have from looking in dimension 3. Make them a bit bigger for you. And if we look at these, let's take a look at the first one. So the first one, so there's 3 non-parallel planes, and they all have a common intersection consisting of one point, that purple dot right there in the middle. So this has one point in the solution set. If we look at the next one to the right, this one has an empty solution set because the 3 planes, although each one intersects another plane, not all 3 of them intersect in the same place. So there's no common intersection of all of them. So that means that the defining equations don't have one single common solution. Same thing with this one over here on the far right. This also has no solutions. Those 2 top planes are supposed to be parallel, so they don't intersect anywhere. Now, if we go down to the next row, well, now we have that there's this entire line's worth of solutions going right through the middle where all 3 of those planes have a common intersection. And so there's an infinite number of solutions right there. If we have 3 parallel planes, then there's definitely going to be no solutions. And if we have 3 parallel planes that actually all happen to be the same plane, then it turns out that we have infinitely many solutions. And in this case, we actually have a 2-dimensional set of solutions, right? Because every point in the plane is going to be a solution. Over here, every point in the line is a plane, so there's infinitely many, but it's a 1-dimensional infinite set as opposed to a 2-dimensional infinite set. And we'll be more precise about what we mean by dimensionality later on in the course. But for now, the takeaway is just to say that, well, there's an entire line's worth of solutions in the first case and an entire plane's worth of solutions in the second case, and both of those contain infinitely many points.